Thank you for joining me. Today we're going to look at how to optimize your reaction chemistry. We'll be using a spreadsheet to understand kinetics of reactions, rate constants, mechanism, solvent effects, and how to green your processes. We'll be looking at this reaction here. It's an azomycal addition reaction between dimethyl itaconate and piperidine. The published article is available at the link above, as well as the separate spreadsheet files that we'll be using today. And there's also some additional sources you might want to use to explain some of the concepts in more detail. This is the front sheet of the spreadsheet. It gives a quick summary of the different tabs that we're going to be using today. We're going to progress through them one by one, and I'll explain how to use them and how to analyze the data. So the data entry sheet here gives you the chance to input your data that you might have collected from your reaction. You can do this by GC or NMR, measuring component concentrations over time. In this case, we will start by entering the names of the reactants and the product. We have an azomycal addition reaction between dimethyl itaconate and piperidine. If you have a catalyst, you can choose the options to the right, where you can choose a Y for yes. In this case, we don't have a catalyst. Then below, you enter your times and concentrations. So ordinarily, you will start with time 0 to start. This will prompt you to add a temperature and a solvent. So our first data set will be at 30 degrees Celsius, and the drop-down menu here will allow you to choose a solvent. The first reaction I performed here was in ethanol. At time 0 we don't have any product yet, so that's a 0, and the initial reactant concentrations are 0.6 molar. You can now continue to fill in the data sheet. Where you have yellow cells is where you need to input more data. So now I've completed the data set. If I scroll down, you'll see that we have different data sets all listed consecutively. Every time you have a t equals 0, again you're prompted to add temperature and solvent. In the case of this version of the spreadsheet, this works with Microsoft 365. You can add repeat reactions. You don't have to measure the concentration of the reactants. That can be derived from the amount of product at any one time. If you have a catalyst, the same applies. If you don't measure the concentration of the catalyst as you go, the initial concentration will be used throughout. This data set varies the concentrations of the reactants, the temperature and the solvent, so we get a full analysis of the reaction, which will be explained as we go along. In the next worksheet, we'll be looking at conversion with time. We can compare our different experiments. They're listed in the table below here. So this is extracted from the previous worksheet. So as we go down, see that we've had a combination of different concentrations, solvents and temperatures, 38 different reactions in total. In the top here, again in the yellow cells, which are editable, I can choose some different reactions to compare. So in this case, I can use the drop-down menu and I'll choose reaction number 1. The basic conditions are listed here. If I then compare that to reactions 5 and 8, we have the same initial reagent concentrations, the same temperature, but in different solvents. If I scroll down, the top chart here will just show the different conversions with time. So we can see the reaction 1 in ethanol proceeded the fastest, and the reaction in THF, tetrahydrofuran, was the slowest. Below this chart, there's a second graph here. This will show you the information from the first experiment that you select. It will show the concentrations of the product, which are the dark blue circles, but also it will show you the concentrations of the reactants A and B. We don't have a reactant C, so that's on the bottom here. In the kinetics tab, we can now look at the order of reaction with respect to each reaction component. In the yellow cells here, we can choose experiments to analyze. Initially, you probably won't know if the temperature of the solvent changes the order of reaction. In this case, I know that the temperature does not change the order of reaction, so I can choose no here. This simplifies the data entry as we go along. but to start off with, I recommend you maintain the yes, the Y option and those cells there. So if I choose our first reaction in ethanol, what we see on the charts are data points from all the reactions that involve ethanol at 30 degrees with data sets with different initial reagent concentrations. This process is called variable time normalized analysis, and the objective is to get the data points to overlap, at which point you've achieved the correct order of reaction. So the first two charts show the concentration of the product on the y-axis. On the x-axis, you have a function of the concentration of your reagent and how that changes with time. And the idea that we need to proceed with now is to then input potential order of reaction in the table below. And as I said, if we get overlap between the data sets, then we have our correct order of reaction. So at the moment, our orders are blank, which is the same as if it was a zero order reaction. No change. If I enter 1, then you see we have overlap. Now, we're not expecting a linear chart here, we're just looking for overlap of data points. For the second chart, this is the order of reaction with respect to piperidine. Again, we're at zero order, we don't have overlap. If I enter 1, now we have a nice overlap of the data points. So we can say confidently now that this reaction, when in ethanol, is first order with respect to dimethyl articonate and first order with respect to piperidine. The chart that involves reagent C is blank, we don't have a reagent C. The last chart on the right is a combination of our different concentrations and orders of reaction, and this will be a linear graph when we have the correct orders of reaction, and the gradient of which gives us our rate constant, and as provided again below the charts. So we need to repeat the process for different combinations of solvent and temperature. If we take the example of dimethyl sulfoxide, again, we can try 1 as an order, and we get decent overlap there. For piperidine, if we try 1, you see that we don't have overlap between the data sets, so we have a different order of reaction here. If I try 2, then we get the correct overlap, and again we have our rate constant derived from the graph on the right. If I do one more example for you, in isopropanol, if we go to the yellow highlighted cell, I can choose 1 as the order of reaction for reagent A, dimethyl articonate, and we get the overlap as expected. If I choose 1 for the order with respect to piperidine, we don't get overlap. If I try 2, again we don't have a good overlap as well. So, and we can continue doing different integers, and we're getting further away from a overlap here. So what we have indeed is a partial order of reaction, and a good approximation is 1.6. Now we have 3 different reactions and different solvents and 3 different mechanisms. In the azomycal addition of dimethyl articonate and piperidine, there are a multitude of pathways the reaction can proceed through to get to the final product, which is labelled number 5. In the presence of a Lewis acid, the 1,4 addition is common, which is on the right-hand side. In the absence of a catalyst, the 1,2 addition mechanism on the left-hand side dominates. There are 2 options to stabilize the intermediates on the way to the product. There is an alcohol-assisted route in the presence of alcohol solvents, but if you have an aprotic solvent, then we proceed through a trimolecular mechanism, which is pathway A on this slide here. In relation to our own kinetic data, we see that in ethanol, for example, we have an alcohol-assisted route. It's a biomolecular reaction. The order of reaction with respect to piperidine is 1. In aprotic solvents, we have an order of reaction of 2 with respect to piperidine and trimolecular overall. In isopropanol, we have a non-integer partial order of reaction of 1.6 with respect to piperidine, and so both pathways A and B are in operation at the same time. So we can infer they have fairly similar energies of activation. I have now completed the data set, entering the different orders of reaction. You will notice in the summary of rate constants on the right that sometimes you won't necessarily have all the data necessary to determine the order of reaction with respect to the individual reagents. but just with one data set will allow you to determine the rate of reaction if you assume that you have the correct orders of reaction, and you can derive this from obtaining a straight line. So in the case of DMF, dimethylformamide, if I have different orders of reaction, then you see I deviate from a linear graph. So from the knowledge I have of the different solvents and their orders of reaction, we can presume what the order of reaction is to derive the rate constant with minimal data. In the activation parameters tab, if you have varied the temperature of your reaction and monitored the kinetics, we can then derive the enthalpy and entropy of activation and gain more information on the mechanism of the reaction. In this case, we have data for 3 solvents. We have ethanol, for example, and now we generate the graph based on the Irving equation. So the gradient of this chart is proportional to the enthalpy of activation, and the intercept on the y-axis is proportional to the entropy of activation. And these values will appear here. If you have investigated the effect of solvent on your reaction, we can investigate the solvent effect in this tab here. Now, solvent effects are dependent on temperature and the mechanism of the reaction. So in this case, we shall analyze the trimolecular reaction, which is first order with respect to dimethyl octaconate, and second order with respect to piperidine. We only have one applicable temperature, which is at 30 degrees. Now, what we're going to do here is to derive predicted rate constants based on the polarity of the solvent. And the first way we can do this is by trial and error. So we have 4 parameters here which relate to the way that the solvent can interact with the products, and in this case the activated complex, and that will change the rate of reaction. Alpha, beta and pi star are known as Kamlet-Taft parameters. So these will correlate to the rate constant. If we input a value here, so let's just put a 1 for hydrogen bond donating ability, we don't have a very good correlation. What is happening here is that we are making an equation based on the hydrogen bond donating ability of the solvent, and that is trying to derive the correlation with the experimental rate constants. But we don't have a good correlation here. If we try hydrogen bond accepting ability, a much better correlation. So we're now getting to a point where we can predict the rate constant based on the polarity of the solvent, specifically the hydrogen bond accepting ability of the solvent. If we remove that and we try a correlation with dipolarity, we also get quite a decent correlation as well. So we might want to try both parameters. And this is looking very good now. So our experimental rate constant can be derived as a function of the dipolarity of the solvent and the hydrogen bond accepting ability. Now this is only an approximation, we're just entering different coefficients. They are adjusted on the right of the yellow cells. What we can do is we can use the data analysis functions of Excel in order to make a more accurate coefficient. If you go to the Data tab, you will need to install the data analysis package. Once you've done that, you can find a regression option. And our Y range will be the experimental rate constants, which are listed below here. So I shall highlight them for the applicable solvents. Now we want to make a correlation based on beta and pi star, which is our hydrogen bond accepting ability and dipolarity. So I shall highlight them. A data table will be produced, and we need the space for that. So I shall have it in this area here on the spreadsheet. And then we get this data analysis here. So this variable here is beta, and this will be pi star. Coefficients are listed here. And now I can just add these to this section here. 3.24, 3.83. So this is our optimized relationship here. Information you get in this table, it gives you the R² value. It also gives you the p-value. So the p-value represents the statistical significance of your variables, and a low value is good. So ideally we want to have values between 0 and 0.1 are ideal. Because this is an empirical relationship, you won't get super accurate results all the time. It also depends on the number of solvents that you've used. 6 is probably the minimum that you want to use. If we scroll down here at the bottom of the slide here, then we have the list of solvents, the experimental rate constant as a natural logarithm, what we can predict from our relationship with beta and pi star. We have the Kamat-Taft parameters here. We also have here is a greenness rating system. So S relates to safety of the solvent, H relates to health hazards, and E relates to the environment and also the technological impact of using the solvent. So solvents with high boiling points will get a worse score, and that's to do with the energy involved to distill solvents for purification. If you want more information on the solvent selection guide, the link was earlier in the video. For now, I'll just briefly describe that low values are greener, so they're better for the environment, safety, and reduced hazards. 10 is the highest value, so we want to avoid the high values and we want to employ solvents with lower values to have a greener reaction. The charts at the top are just a convenient way of showing the relationship between an efficient reaction with a high rate constant and also a green solvent, the solvent being the majority of the reaction mass. And so if we employ a green solvent, we go a long way to having a greener reaction. Now we have the 3 parameters for safety, health, and environment. So we can look at this as either adding up these values or we can take the maximum value. So if we focus on the maximum value, so we really want to avoid, say, the red values here. Say we have for tetrahydrofuran, chloroform, DMF, dimethylformamide, and also the high boiling point of polyethylene glycol is also an issue for purification after reactions. On this graph here, we can rescale to make it more appropriate for our reaction. So if we use -4 as the maximum, then ideally what we want to get here is solvents in the green area, which is quite ambitious. And here we have one solvent which is in the yellow area, that being dimethyl sulfoxide. So arguably you could say with dimethyl sulfoxide, also known as DMSO, we have quite a fast reaction, the rate constant is high, and also we have minimal hazards. If you wanted to pursue a greener solvent, we can also look at different mechanisms. So remember, if we go back to the top, this is a trimolecular reaction. Alcohols facilitate the bimolecular reaction, in which case we could then explore greener solvents based on alcohols, which are often greener than aprotic solvents. If you want to proceed in solvent selection to identify a greener solvent for your reaction, we can then expand this search to outside of your experimental data set. So what we have here, if we scroll down, we have a list of solvents with predicted rate constants derived from the previous worksheet. So what we've got here is a recommendation of dimethylpropylene from our data set. There's about 100 solvents in this list, which has been extracted here for the highest performing 15. Now, this solvent is not particularly green. We have moderate health hazards, and we also have the problem of a high boiling point, resulting in a high score here in this category. So what we can do here is to refine the search a bit more. We can exclude certain different types of solvents. So if we get rid of acids, for example, so we're using a base as one of our reactants, and so an acid is going to neutralize the base and therefore make it less effective. We can also get rid of other bases which might compete with the intended reaction. Nucleophiles, so in this case, this reaction does tolerate solvents which are nucleophiles, say alcohols for example, but in other examples of micro additions you'll get a competitive reaction, so we could remove these as well. And again, we could remove potentially reactive solvents, so esters and ketones for example. And so we have a new list now which now involves just the solvents which are potentially suitable. We still have to contend with what are the greener solvents. So the solvent that we tried before, dimethyl sulfoxide, is still rated pretty highly. But remember, this is based on aprotic solvents in the trimolecular reaction. If you wish, you can then also look at the solvents which have been excluded. So now you see there are some alcohol solvents. We've excluded these because they are nucleophiles. The final thing I wanted to show you was how to use metrics to also improve your chemistry. So here we're going to examine a particular reaction, and we're going to choose ethanol as our solvent. So I'll pick it from the drop-down list. Now I can look at the performance of the reaction at different temperatures. For now I'm going to start with some familiar conditions, so I'm going to choose 30 degrees. I'm going to choose more often the starting conditions, 0.6 molar of the reactants. And here you'll be given a hint of what orders of reaction are appropriate. So I'm going to choose the bimolecular reaction. And the drop-down list will provide appropriate orders of reaction. If I want to look at the variation in temperature, I need to input our enthalpy and entropy of activation. So we looked at this before, and I can type in the values here. Okay. Now what I can do is I can examine what is the predicted performance of the reaction. So if you input characteristics and parameters from an experimental data set, so the solvent, temperature, initial reagent conditions, you will get the blue circles on this graph here, and they represent the experimental data. The orange data points, the smaller solid colored circles, they are representing a predicted conversion with time. And I can also look at some specific points in the reaction here. So say after 12 hours, I would expect 94% conversion. I can then go on to investigate other situations. So I could screen different solvents based on the solvent effects that we looked at before, or I can change the temperature. So if I increase from 30 to 50 degrees, then I lose my experimental data set because we no longer have a corresponding experimental values, but I can see how that would change the rate of reaction. I could then, for example, compare that change of temperature to increase in the reagent concentrations, and it might be that it would be more beneficial to have a high concentration reaction and then get a faster rate of reaction that way than to increase the temperature of the reaction. So you can explore those variables with this data sheet there. The other thing we can do is then see how that influences the metrics of the reaction. So on the right hand side I need to put a bit more information about the reagents. So dimethyl aldeconate, if I add its molecular mass, same for pyridine. Also I need to tell the software the stoichiometry of the reaction, which is 1:1. Addition reaction, so the product has a mass corresponding to both the reagents. And then to work out the mass metrics, I need to have a volume of solvent. So if I chose 22 milliliters, for example, about 10 grams of product. Now, what we see in the graph here, if I had the final stoichiometry, are some mass-based metrics. So in green chemistry, we focus a lot on minimizing waste, and to minimize waste, you want to increase the yield and also use less of excess reagents, for example. So we have, in this case, 98% predicted yield. That is after 12 hours of this reaction with 2 molar concentrations of both reactants. If I chose to use an excess of one reagent over the other, then again I change the ultimate yield, and also I could do a more realistic duration of the reaction. If we go back to our mass metrics, so the yield is important. That will determine some of the other mass metrics. Independent of that is atom economy on the top right. So this tells you how many of the atoms of your reactants end up in the product. And then we have an addition reaction, and therefore we have 100% atom economy. The lower two graphs relate to the amount of waste that is produced. So in the bottom left, we have reaction mass efficiency, 71%. So if we use an excess of one reagent over another, that excess will become waste. And so we could minimize that by using equimolar starting conditions. We could also leave the reaction going longer, and we get improved mass utilization as we incorporate more reactants into products. Finally, we have optimum efficiency, which is the ratio between reaction mass efficiency and atom economy. Atom economy limits how many of the atoms will end up in the product, and so optimum efficiency will take into account the type of reaction which you're using. And so that is it for the summary of how the spreadsheet works. Again, I'd like to thank you for listening, and please check out the publications and the data which is available online. Thank you.